Right now, at this very moment, you are moving through space at 630 kilometers per second. Not because of Earth's rotation, not because of the orbit of our planet around the Sun, not because our entire solar system is wheeling through the Milky Way at 230 kilometers per second. On top of all of that, something else is dragging you. Something enormous. Something that sits in a direction we can barely see because our own galaxy's disk of dust and gas blocks the view. Something that has been pulling the Milky Way, the Andromeda Galaxy, the Virgo cluster, and approximately 100,000 other galaxies toward it for billions of years. We have been falling toward it since before Earth existed. We are still falling. We cannot stop. And the strangest part, the part that should make you sit very still and think, is that we spent decades unable to see it directly, even though it is the most gravitationally dominant structure within 500 million light-years of us. We knew it was there because of what everything else was doing. We found it the way you find a black hole in a dark room, not by looking at it, but by watching everything around it accelerate toward a point in space and asking what in the universe could possibly be doing that. The story of the Great Attractor begins in the 1980s with a group of 7 astronomers who were trying to do something seemingly straightforward. Measure the distances to a large sample of elliptical galaxies and compare those distances to the velocities those galaxies were moving away from us. The idea was to use this comparison to map the large-scale flow of matter in the local universe. They called themselves the 7 Samurai, an informal but affectionate name that has stuck in the astronomical literature. The 7 were Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lynden Bell, Roberto Turlevich, and Gary Wegner. Working with telescopes in the late 1970s and early 1980s, they measured hundreds of elliptical galaxies in the local universe and used a relationship called the Faber-Jackson relation, which connects the luminosity of an elliptical galaxy to the velocity dispersion of stars within it as a distance indicator. By comparing the measured brightness of galaxies to their true brightness inferred from their stellar dynamics, they could derive accurate distances. And when they plotted those distances against the velocities the galaxies were moving, something extremely strange emerged from the data. The galaxies were not moving in the way they should if the only thing governing their motion were the smooth expansion of the universe. Hubble's law says that in a smooth, uniformly expanding universe, every galaxy moves away from every other galaxy at a rate proportional to the distance between them. The farther apart, the faster the recession. If the universe were perfectly smooth, the data would lie on a straight line when you plotted velocity against distance. The 7 Samurai's data did not lie on a straight line. It showed a systematic deviation, a coherent flow superimposed on the Hubble expansion, as if a vast current were running through this entire region of space, sweeping hundreds of galaxies in the same direction at hundreds of kilometers per second. Every galaxy in the survey appeared to be streaming toward a single point on the sky, a point in the direction of the constellation Centaurus. When the 7 Samurai published their findings in 1988, they estimated that the source of this gravitational anomaly lay at a distance of approximately 250 million light-years, and had a mass equivalent to tens of thousands of galaxies. They named it the Great Attractor. And that name, with its weight of implication, has defined a chapter of cosmology ever since. Here is the first drop in the story, the moment the ground falls away. The direction of the Great Attractor is almost exactly in the plane of the Milky Way. Our galaxy is a disk of stars and gas and dust, roughly 100,000 light-years across and only about 1,000 light-years thick. Seen from our perspective, edge-on when we look toward the center and the periphery of the disk simultaneously. That disk is an extraordinary thing to live inside, dense with stars, beautiful beyond description. But it is also, for astronomers trying to look out at the wider universe, an almost complete obstruction. The gas and dust in the galactic plane absorbs optical light so efficiently that you can't see more than a few thousand light-years in most directions through the disk. Beyond the disk in those directions lies not darkness, but invisibility, the rest of the universe hidden behind a curtain of our own galaxy. Astronomers call this the zone of avoidance, because galaxy surveys simply leave it blank. It is not that nothing is there. It is that we cannot see through our own galaxy to find out what is. The Great Attractor sits, with infuriating precision, almost exactly behind the zone of avoidance. The direction of maximum gravitational pull points into the one region of sky that optical telescopes cannot penetrate. For years, this meant that the object producing the most dominant gravitational influence on our neighborhood of the universe was sitting in a blind spot built into our cosmic address. We could feel the pull. We could map the motion of hundreds of galaxies being drawn toward it. But we could not look directly at it and say, there it is. We had to work around our own obstruction using radio waves and X-rays and infrared light that can penetrate the galactic dust to some degree, slowly peering through the curtain to see what was hiding behind. What eventually emerged from this careful, painstaking effort is both more and less than the name implies. The Great Attractor is not a single massive object. There is no galaxy-eating behemoth sitting at the center of this gravitational influence, no ultra-dense point of matter pulling everything down. What the Great Attractor actually is, and this is something that took years to fully appreciate, is a concentration of mass spread across an enormous volume of space. It is a supercluster, or more precisely, the core region of what has come to be understood as an even larger structure. At the heart of the gravitational overdensity that the Seven Samurai detected is the Norma cluster, also catalogued as Hubble 3627, a rich cluster of several hundred galaxies, roughly 220 million light-years away. The Norma cluster is large and massive by the standards of galaxy clusters, but it is not uniquely extraordinary. It is surrounded by several other clusters and groups of galaxies, and together they constitute the Norma supercluster, which was the best candidate for the source of the anomalous gravitational flow for many years. But here comes the surge back up the track. The Norma supercluster was not enough. When astronomers measured the flow velocities more carefully and mapped more of the local universe, they found that the total mass in the Norma supercluster region could not account for all of the observed motion. Something beyond it further away in the same general direction was also contributing. And in 1989, the year after the Seven Samurai announced the Great Attractor, a different team announced a discovery that changed the scale of the problem entirely. 100 million light-years behind the Great Attractor, a previously underappreciated supercluster came into view. It was named the Shapley Supercluster, after the American astronomer Harlow Shapley, who had catalogued an unusual concentration of galaxies in that direction back in 1930. When modern redshift surveys finally mapped it properly, the Shapley supercluster turned out to be the most massive structure in the observable universe within 1 billion light-years of us. It contains dozens of rich galaxy clusters. Its total mass is estimated at 10 million billion solar masses. It is roughly 600 million light-years away, and its gravitational influence on the surrounding universe is substantial enough that a significant fraction of the flow the Seven Samurai measured is not being caused by the Norma supercluster at all, but by the Shapley supercluster pulling from further out, like an anchor dropped at the far end of a chain. This began the process of revising our understanding of what we actually mean by the Great Attractor. Is it the Norma cluster, the Norma supercluster, the combination of the Norma supercluster and the Shapley supercluster? Is it a broader region of gravitational overdensity that has no clean boundaries? The answer, it turned out, required a completely different way of thinking about our cosmic address. And that new way of thinking arrived in 2014, when a team led by R. Brent Tully at the University of Hawaii published a paper in Nature that redrew the map of the universe around us so comprehensively that it made scientists genuinely stop and reconsider where they lived. The paper was titled The Laniakea Supercluster of Galaxies. Tully and his colleagues used a new technique to map the flow of galaxies across the local universe, not just measuring distances and velocities for individual galaxies, but computing the full three-dimensional velocity field across a volume of space roughly 1 billion light-years across, and then tracing the flow lines, the directions in which galaxies are gravitationally drawn. The cosmic watershed divides where galaxies on one side flow toward one attractor, and galaxies on the other side flow toward a different attractor. What emerged from this mapping was a structure of breathtaking scale. On the largest scales, the flow lines across our region of the universe do not converge on the Norma cluster, or the Norma supercluster, or even the Shapley supercluster. They converge on a single point, a gravitational focus that the flow field defines as the attractor for an enormous volume of space, and the structure drained by this flow. All the galaxies and galaxy clusters that are gravitationally bound to this watershed, all of them pouring inward toward this central point. That structure is what Tully named Laniakea. It means immeasurable heaven in Hawaiian. It contains approximately 100,000 galaxies, including the Milky Way, the Andromeda Galaxy, the Virgo cluster, the Centaurus cluster, the Norma cluster, and dozens of other named structures. It spans 500 million light-years from edge to edge, and its total mass is approximately 100 million billion solar masses, or about 10 to the 17th solar masses in scientific notation. We are not just falling toward the Great Attractor. We are inside a structure that has a great attractor at its heart. The Milky Way is not an outside observer watching matter flow toward some distant anomaly. We are part of the flow. We are participants in it, caught in the watershed of Laniakea, being drawn together with 100,000 other galaxies toward the gravitational center of our own supercluster. The Great Attractor is our home address at the largest scale, the way your street name is your address at the smallest scale. Laniakea is the neighborhood, and at the center of the neighborhood is the pull that defines its boundary. And yet, and here the track drops again, steeply and unexpectedly, Laniakea itself is not the final answer. It was not even the most significant recent discovery about the motion of our galaxy through the cosmos. Because while astronomers were carefully measuring all these flows, pulling our galaxy toward the Shapley supercluster and the Norma cluster, they missed something. They were so focused on the pull that they forgot to look for the push. In 2017, a team led by Yehuda Hoffman at the Hebrew University of Jerusalem published a paper announcing the discovery of what they called the dipole repeller. The paper appeared in Nature Astronomy and caused considerable discussion precisely because of what it proposed: that the coherent motion of the Milky Way and thousands of surrounding galaxies is not simply caused by gravitational attraction toward massive structures. It is also caused by gravitational repulsion from a massive void, an enormous region of space that is dramatically underdense in matter, a region where the average density of galaxies is far below the cosmic mean. In the direction opposite to the Great Attractor, the team found a void spanning hundreds of millions of light-years, a relative emptiness in the cosmic web so large that its gravitational deficit pushes galaxies away from it, just as a massive overdensity pulls them toward it. This is not a violation of physics. Gravity works on density contrasts, not on absolute densities. An underdense region does not attract as strongly as the average surroundings, which means the surrounding matter experiences a net force away from the void and toward the denser regions. In a universe where matter is unevenly distributed, and our universe most definitely is, with a web of filaments and voids and clusters that is far from smooth, voids push just as genuinely as superclusters pull. The dipole repeller and the Shapley supercluster are on opposite sides of the Milky Way, and between them, caught between a push and a pull acting in the same direction, our galaxy is being propelled at the full 630 kilometers per second, peculiar velocity that observations have been measuring since the 1980s. The Great Attractor alone could not account for all of this. The combination of the dipole repeller pushing and the Shapley supercluster pulling with the Norma cluster as an intermediate attractor accounts for most of it. We are being squeezed through space by the cosmic web itself. Sit with that image for a moment. You are not just moving because of gravity. You are moving because of the shape of the universe at the larger scales. The distribution of matter across hundreds of millions of light-years. The underdense voids leaving gaps that the cosmic web's filaments fill unevenly. The overdense superclusters sitting at the intersections of those filaments. The Milky Way's motion through space is a readout of cosmic structure itself. Every kilometer per second of our peculiar velocity is a statement about how matter is distributed across a volume of space so large that light has been crossing it for hundreds of millions of years. Now, let us talk about the zone of avoidance, because this story has a twist that was discovered in 2017. An entire supercluster that was sitting hidden behind the Milky Way's disk, and nobody knew it was there until researchers pointed radio telescopes through the galactic plane and mapped galaxies that infrared surveys had missed. The discovery was announced by a team led by René Kraan-Korteweg at the University of Cape Town, and it was one of those rare moments in astronomy when the universe turns out to be significantly stranger and more structured than the models predicted. They called it the Vela supercluster. It is located at approximately 800 million light-years away, sitting almost directly in the zone of avoidance in the direction of the constellation Vela. Its mass is estimated at about 1 quadrillion solar masses. It had not been included in any of the calculations of local peculiar velocity flows because nobody knew it existed. When it was factored into the models, the fit between observed galaxy motions and the predicted gravitational sources improved. But it also revealed that our models of local large-scale structure were incomplete in ways that nobody had fully appreciated. Hidden behind our own galaxy, a supercluster of significant mass had been quietly exerting gravitational influence on our neighbourhood for billions of years without ever appearing in a catalogue. The zone of avoidance, in other words, is not an absence of content. It is a concealment of content. And the concealment is imperfect enough, with radio, infrared and X-ray observations, that we have been gradually pulling back the curtain. But the basic fact remains. We are living inside a galaxy that physically obstructs our view of the most gravitationally important direction in our cosmic environment. If the Milky Way were transparent, or if we lived outside it and looked at it from the side, the Great Attractor would be one of the most studied and prominent features of the local universe. Instead, it took us until the late 1980s to be confident it existed, and until the 2010s to map it with any precision. Let us step back further. Let us get the whole picture, because the story of what is dragging our galaxy through the cosmos does not end at the Shapley supercluster or the Vela supercluster or Laniakea. There is a chapter to this story that goes beyond what standard gravitational analysis can explain, a chapter that is either one of the most extraordinary discoveries in modern cosmology, or one of the most tenacious systematic errors in the history of observational astronomy, and nobody has yet been able to decide which. It is called dark flow, and it began in 2008 when Alexander Kashlinsky, a NASA astrophysicist at the Goddard Space Flight Center, published a paper making a claim that, if true, would mean that something beyond the observable universe is dragging our entire cosmos in a specific direction. Not just the Milky Way, not just Laniakea, not just the region affected by the Shapley supercluster. Everything we can see, all the galaxy clusters out to the edge of the observable universe, billions of light-years away, all of them moving coherently toward a specific point on the sky. Here is how Kashlinsky and his team found this. They used the kinetic Sunyaev-Zeldovich effect, a phenomenon in which the cosmic microwave background radiation, the faint afterglow of the Big Bang, the oldest light in the universe, is slightly distorted by the bulk motion of galaxy clusters passing through it. When a hot plasma of electrons in a galaxy cluster moves toward us, it scatters the microwave background photons and imparts a slight blue shift to them in that direction. When it moves away, it imparts a slight red shift. By measuring these subtle temperature shifts across thousands of galaxy clusters, Kashlinski's team were effectively measuring whether those clusters were moving toward or away from us. And they found that the clusters, spread across billions of light-years, were not moving randomly as they should if the only gravitational influences were the known large-scale structures within the observable universe. They were moving coherently in a specific direction. All of them. A bulk flow far larger and more uniform than any known attractor within the observable universe could produce. Kashlinski named this coherent motion dark flow, by analogy with dark matter and dark energy, forces and phenomena that affect the observable universe but whose origin lies beyond what we can directly see or measure. His interpretation was extraordinary. The coherent flow was being caused by something outside the observable universe, beyond the cosmic horizon, in a region from which light has not yet had time to reach us since the Big Bang. Some concentration of matter of stupendous size, sitting in a causally disconnected region of the cosmos, was exerting a gravitational tug on everything we can see through its influence on the primordial density field, and everything within our observable universe was streaming toward it. The reaction from the broader cosmological community was skeptical, deeply skeptical. If dark flow is real, it implies that the universe beyond our horizon is not statistically similar to the universe within it, that there are structures out there, beyond the reach of any telescope we will ever build, that are fundamentally different in their distribution from what we observe nearby. This would be in tension with the cosmological principle, the foundational assumption of modern cosmology, that the universe is approximately homogeneous and isotropic on the largest scales, the same in all directions, the same everywhere you look when you average over volumes large enough to smooth out local fluctuations. A dark flow caused by a super-horizon structure would be a violation of this principle, or at least a severe qualification of it, and most cosmologists are extremely reluctant to abandon the cosmological principle without overwhelming evidence. Subsequent analyses of Planck satellite data by independent teams have not confirmed dark flow. They have placed upper limits on the magnitude of any coherent bulk flow that are significantly smaller than what Kashlinski measured. Kashlinski has maintained that his measurement stands, that the systematic errors his critics identify do not account for the discrepancy, and the debate in the literature has continued for 15 years without resolution. The dark flow may be real. It may be a systematic error in the analysis. The instruments we have and the techniques we are using are not yet precise enough to definitively settle the question. But the possibility that something beyond our observable universe is pulling everything we can see, that the 630 kilometers per second of our peculiar velocity is not the bottom of the well, but just one step of a journey towards something our telescopes will never reach. That possibility remains stubbornly within the error bars of our measurements. Let us take a moment to appreciate what it means that we are moving at 630 kilometers per second through the universe. In 1 second, the Milky Way covers 630 kilometers. In 1 minute, 37,800 kilometers. In 1 hour, 2,268,000 kilometers. In 1 day, 54 million kilometers. In 1 year, about 20 billion kilometers. This is 3 times the distance between the Sun and Neptune covered in a single Earth year, simply by the gravitational flow of our galaxy toward the Great Attractor. It is a breathtaking velocity when you work it out in human terms. And yet, given the distances involved, the Norma cluster is 220 million light-years away, a light-year being approximately 9.5 trillion kilometers. At 630 kilometers per second, it would take our galaxy roughly 330 billion years to reach the Norma cluster if nothing changed, which is more than 20 times the current age of the universe. But things will change. And here is the part of the story that most presentations of the Great Attractor leave out, the part that reframes everything you have just learned and drops it into a completely different context. The universe is not just filled with matter, it is filled with something else, something we call dark energy. And dark energy does not play nice with the flow toward the Great Attractor. Dark energy was discovered in 1998 when 2 independent teams of astronomers, the High Z Supernova Search Team and the Supernova Cosmology Project, measured the distances to Type 1a supernova in distant galaxies, and found that the universe's expansion is not slowing down as they expected. It is accelerating. Galaxies are not just flying apart. They are flying apart faster and faster with each passing year. The force driving this acceleration, which we attribute to dark energy, constitutes approximately 68% of the total energy content of the universe. Dark matter makes up approximately 27%. Ordinary matter, atoms, molecules, stars, gas, everything we have ever touched or seen or built telescopes to detect, makes up approximately 5%. We are the rounding error in the cosmic budget. Dark energy has a remarkable property. It does not dilute as the universe expands. While the density of matter decreases as the universe grows larger, the same number of atoms spread over a larger volume, dark energy maintains a constant energy density per unit volume. This means that as the universe expands, dark energy becomes progressively more dominant relative to matter. In the distant past, when the universe was much smaller and matter was packed more densely, dark energy was a negligible component of the cosmic energy budget, and matter's gravity was the dominant force shaping the large-scale structure. As the universe expanded, dark energy became more important. Today, it dominates. And in the future, it will be overwhelmingly dominant. What this means for the Great Attractor Laniakea, the Shapley supercluster, and the entire narrative of our galaxy's flow through the cosmos is this. It is a race that gravity is losing. The gravitational attraction of all these structures, the Norma cluster, the Norma supercluster, the Shapley supercluster, the entire Laniakea watershed, is pulling the Milky Way and its neighbours toward a common centre. But dark energy is simultaneously pushing the universe apart. For galaxy clusters that are very close together, gravity wins. They are already bound and will remain bound even as the universe expands. The Milky Way and the Andromeda Galaxy will collide and merge in approximately 4.5 billion years, because they are gravitationally bound to each other, and dark energy cannot override that bond at these distances. The Virgo cluster at 60 million light-years is likely gravitationally bound to the local group and will eventually merge with it on a timescale of tens of billions of years. But the Norma cluster at 220 million light-years and the Shapley supercluster at 600 million light-years, these are different. At those distances, the expansion of the universe, amplified by dark energy, may be winning. The peculiar velocity of our galaxy toward the Great Attractor is 630 kilometers per second. But the rate at which the expansion of the universe is separating us from objects at those distances is also hundreds of kilometers per second, and it is accelerating. The detailed calculation depends on the exact dark energy equation of state. How dark energy's density changes or does not change with the expansion of the universe, and on the precise mass distributions of all these structures. But the rough conclusion is sobering. The Milky Way may never reach the Great Attractor. We are falling toward it, but we are falling on an accelerating treadmill, and the question of whether our peculiar velocity is large enough to overcome the expansion at those distances has no simple yes or no answer with current data. What we do know is this: the universe will not always look the way it does now. The cosmic web that we see today, the filaments of galaxies, the voids between them, the superclusters at the intersections, is a temporary structure. In tens of billions of years, the accelerating expansion driven by dark energy will stretch the universe to the point where galaxies outside our local gravitationally bound neighborhood become unreachable. Not just very far away, but receding faster than light can travel, causally disconnected from us forever. An astronomer living in a galaxy 10 billion years from now in a universe shaped by billions, more years of dark energy domination, will look out and see a dramatically simpler cosmos. Not the rich web we see today with its millions of charted galaxies, but a mostly dark, expanding emptiness with only the immediate gravitational family, the merged remnants of our local group, visible in any direction. In that future universe, there will be no way to measure the cosmic microwave background precisely, because it will be redshifted to wavelengths too long to detect. There will be no way to measure the Hubble constant, because there will be no distant galaxies to measure it against. The evidence for the Big Bang, the evidence for dark energy, the evidence for the large-scale structure of the cosmic web, all of it will be erased by the expansion. A civilization arising in that distant future would have no way to reconstruct the universe we see today from the evidence available to them. They would be surrounded by an apparently static, dark, featureless cosmos, and have no way of knowing that it was once a dynamic, web-filled universe filled with billions of galaxies. They would get cosmology badly wrong, not because they were stupid, but because the universe would have hidden the evidence. This is a thought that should genuinely disturb you, because it raises an uncomfortable corollary. We live in what cosmologists are beginning to call a privileged epoch, a period in cosmic history when the universe is old enough for structure to have formed and for stars and planets and observers to exist, but young enough for the large-scale structure to still be visible and mappable. We can see the cosmic web. We can measure dark energy. We can detect the microwave background. We can map the flows of galaxies across hundreds of millions of light years. In the deep future, none of this will be possible. And if we are in a privileged epoch for observation, what does that imply about epochs before ours? What were the physics doing in the early universe, the first billion years, the first 100 million years, that we cannot directly observe now, that the expansion has already hidden from us? The Great Attractor is a question that opens outward indefinitely. Let us return to something concrete. How do we actually measure the motion of our galaxy toward the Great Attractor? The answer involves the cosmic microwave background, the CMB, and a measurement that is in some ways the most remarkable observation in all of astronomy. The CMB is the thermal afterglow of the hot plasma that filled the universe until about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, and the photons were freed to travel. That radiation has been traveling ever since, cooling as the universe expanded, and today it arrives from all directions as a faint glow of microwave radiation at a temperature of 2.725 Kelvin, barely above absolute zero. It is the oldest light in the universe, and it is extraordinarily uniform. The temperature is the same in every direction to a precision of 1 part in 100,000. But it is not perfectly uniform. And one of the most prominent patterns in the CMB is something called the dipole anisotropy. The CMB dipole is the observation that the CMB is slightly hotter in one direction and slightly cooler in the opposite direction. The temperature difference is about 3.3 millikelvin, a few thousandths of a degree, but it is unmistakable, and it is caused by the Doppler effect. We are moving through space toward the hot side and away from the cool side, and that motion blue shifts the photons arriving from ahead, and red shifts those arriving from behind. By measuring the magnitude and direction of the CMB dipole, we can directly measure our total velocity through space relative to the rest frame of the cosmic microwave background, which is approximately the rest frame of the universe as a whole. The measurement is exquisitely precise. We are moving at 627 kilometers per second toward a point on the sky in the direction of the constellation Centaurus, which is also the direction of the Great Attractor. This is one of the most direct, most unambiguous measurements in all of cosmology. 627 kilometers per second. That is our speed relative to the universe, and the direction toward Centaurus, toward the Great Attractor, toward the Norma cluster and the Shapley supercluster behind it, points directly into the gravitational landscape we have been describing. The CMB dipole is not just an abstract measurement. It is the imprint of the Great Attractor on the oldest light in the universe, the echo of 4 billion years of gravitational drift preserved in microwaves from the edge of the observable cosmos. But here is something that very few popular accounts of the Great Attractor mention, something that changes the texture of the story in an important way. The motion measured by the CMB dipole is our total peculiar velocity, the combination of all the gravitational influences acting on our galaxy, the local group pulling us toward Andromeda, the Virgo cluster pulling us gravitationally, the Laniakea supercluster pulling us toward the Norma region, the Shapley supercluster pulling from behind the Norma cluster, the Vela supercluster pulling from its hidden position, the dipole repeller pushing from the opposite side, and possibly the dark flow from beyond the observable universe, if that measurement is correct. All of these, summed together, give us 627 kilometers per second in the direction of Centaurus. Disentangling which source is responsible for which fraction of this velocity is one of the central technical challenges of observational cosmology, and the numbers I have given are best current estimates that have changed substantially over the past 4 decades, and will likely change again. The Virgo cluster, for instance, contributes something in the range of 200 to 300 kilometers per second to our peculiar velocity. The Virgo cluster is the nearest large galaxy cluster to us, approximately 53 million light-years away in the direction of the constellation Virgo, and it contains roughly 1,300 galaxies. Our own local group, the Milky Way, Andromeda, and the 50 or so smaller galaxies gravitationally bound to them, is located at the periphery of the Virgo supercluster, which is now understood to be a substructure within Laniakea. The Virgo cluster's pull on us has been adding to our motion for billions of years, and without the larger-scale flows it would be the dominant component of our peculiar velocity. Beyond Virgo, the Centaurus cluster, approximately 160 million light-years away, in the direction where the Great Attractor's influence is most clearly seen, contributes another significant fraction. The Norma cluster and the associated density enhancement in the Norma supercluster contribute more. The Shapley supercluster at 600 million light-years contributes a velocity component that independent analyses estimate at between 100 and 200 kilometers per second. And the dipole repeller pushes from the opposite side by an amount roughly comparable to the Shapley pull. Each of these contributions has been measured and remeasured as observational data have improved, and the story has steadily become richer and more complex with each revision. There is another angle to all of this that I want to bring in, because it changes the emotional register of the story. What does our position within this gravitational landscape mean for our long-term future? Not the short-term future of civilization, which has plenty of other threats to contend with. The very long-term future, the cosmological future. We are, as I mentioned, part of Laniakea, a supercluster of about 100,000 galaxies spanning 500 million light-years. Laniakea is not gravitationally bound. This is an important distinction. The Milky Way and Andromeda are gravitationally bound. They will merge. The local group is gravitationally bound. It will remain a coherent structure. The Virgo cluster is probably bound, but Laniakea as a whole is not. The outer parts of Laniakea are already being stretched apart by the expansion of the universe, and in the far future, Laniakea will dissolve. Its constituent galaxy clusters will drift apart, each becoming an isolated island in an increasingly dark and empty cosmos. The flow lines that Tully and his team used to define Laniakea's boundaries in 2014 are current flow lines, the direction galaxies are moving today. They are not a promise that those galaxies will ever arrive at the same destination, or that the structure will remain coherent long enough to matter. Our ultimate fate on cosmological timescales is isolation. The local group merged into a single massive galaxy containing the stars of both the Milky Way and Andromeda. Astronomers have nicknamed this future galaxy Milkdromeda, or more recently, Andromilky, will find itself increasingly alone as the universe expands. The Virgo cluster and the wider Virgo supercluster membership may remain gravitationally associated with the local group remnant for tens of billions of years. But Laniakea's broader membership will disperse. The Norma cluster will eventually be beyond reach. The Shapley supercluster will recede so fast it effectively ceases to exist in our causal future. The Great Attractor's pull will be overcome by the expansion, not because gravity weakens, but because the expansion carries the destination beyond the reach of gravity's influence. We are, in other words, in the middle of a story that has a definite and somewhat melancholy ending. The motion our galaxy is making today, the 627 kilometers per second toward the Great Attractor, the fall through Laniakea toward the Norma region, the long, slow drift shaped by the Shapley supercluster and the Vela supercluster, and the dipole repeller. All of this is happening in the last cosmological chapter in which such motion matters. In the deep future, the universe will be too expanded, too dark, too empty for a galaxy to have meaningful, peculiar velocity relative to any other galaxy. There will simply be the expanding void. Now, let us talk about something that rarely appears in popular discussions of the Great Attractor, but is, scientifically, one of the most important recent developments in this whole story. It concerns how the universe's large-scale structure formed in the first place, and how the positions of the superclusters and voids that are shaping our galaxy's motion today were imprinted in the first tiny fraction of a second after the Big Bang. The universe began in a state of extraordinary uniformity. In the first fraction of a second, a period called inflation, the universe underwent a phase of exponential expansion that smoothed out any initial inhomogeneities, stretched quantum fluctuations to macroscopic scales, and produced a nearly but not perfectly uniform distribution of energy. The not perfectly is everything. The tiny density perturbations generated by quantum fluctuations during inflation are the seeds of all the structure we see in the universe today. Those fluctuations were small at first, variations of roughly 1 part in 100,000 in the density of matter. But over the approximately 13.8 billion years since the Big Bang, gravity has amplified those fluctuations relentlessly. Regions that were slightly denser than average attracted more matter, became denser still, attracted even more matter, and eventually collapsed to form galaxies, galaxy clusters, and superclusters. Regions that were slightly less dense than average lost matter to their denser neighbours, became less dense still, and eventually evolved into the voids that fill most of the volume of the universe. The Norma supercluster exists because 13.8 billion years ago, in the region of space it now occupies, there was a tiny positive fluctuation in the density of matter, a quantum hiccup in the inflationary field that made that region marginally denser than the surrounding universe. That marginal density excess amplified by billions of years of gravitational attraction, produced the most gravitationally dominant structure in our cosmic neighbourhood. The dipole-repeller void exists because in that region there was a slight density deficit, a slightly emptier patch in the quantum distribution that grew into one of the largest voids in the observable universe. And our galaxy, formed in a region of intermediate density, finds itself today caught between these two extremes, being pushed by the void and pulled by the overdensity, moving at 627 kilometers per second toward the most massive structure in our corner of the cosmos. The whole story, from the inflationary quantum fluctuation 400 billion seconds ago to the 627 kilometers per second measured by satellite observations of the CMB, is a single unbroken chain of physical causation. The universe's structure today is written entirely in the initial conditions, amplified and elaborated by billions of years of gravity and dark energy acting on matter. There are no mysteries in the mechanism, only mysteries in the initial conditions themselves. Why the quantum fluctuations had the particular spectrum they had, what set the amplitude of the perturbations, why the ratio of matter to dark energy has the values it has, and most profoundly, what happened before inflation, or what caused inflation to begin. These are questions without current answers, but they are questions that the Great Attractor makes concrete. The Great Attractor is not a curiosity, not a cosmic coincidence, not an anomaly to be explained away. It is the visible consequence of physics from the first moments of the universe, the gravitational echo of a quantum fluctuation from before any stars existed, the structure that was written into space-time before the first atom formed. And our galaxy has been falling toward it in response to that ancient perturbation for as long as our galaxy has existed. We are also learning, through the extraordinary precision of modern galaxy surveys, through the Dark Energy Survey, through the Baryon Oscillation Spectroscopic Survey, through the upcoming Euclid Space Telescope and the Nancy Grace Roman Space Telescope, that our neighbourhood of the universe is not typical. The region within about 1 billion light-years of us appears to be moderately underdense relative to the cosmic average. Some analyses suggest we live in something that might be called a local void, not as dramatic as the dipole repeller, but a region where the density of galaxies is perhaps 20 to 30% below the cosmic mean. If true, this would have implications for the Hubble tension, the discrepancy between different measurements of the expansion rate of the universe, because living in an underdense region would mean that the local expansion rate appears faster than the global average, which is exactly what the tension observationally shows. We might be in a local bubble of underdensity, surrounded by denser filaments and walls, and the Hubble tension might be partly explained by our non-average cosmic address. This is a live and active research question as of the mid-2020s. Multiple groups are working on it with different data sets and different analysis techniques, and the results are not yet convergent. But the possibility that our galaxy's location in the cosmic web, not just our motion toward the Great Attractor, but the particular void we appear to inhabit, is affecting our measurements of fundamental cosmological parameters, is a remarkable and somewhat humbling idea. We are not disinterested observers of the universe. We are embedded in it, at a particular location in its structure, and that location affects what we see and how we interpret it. The James Webb Space Telescope, launched on Christmas Day of 2021, has been adding a new dimension to this story. In its first 2 years of science operations, Webb revealed that the early universe produced massive, structured galaxies far earlier than standard cosmological models predicted. Galaxies with stellar masses comparable to the Milky Way were found at redshifts corresponding to less than 500 million years after the Big Bang, at a time when the Standard Model suggested the universe had barely begun forming the seeds of such structures. These findings are not yet definitively in conflict with the standard cosmological model. Various explanations involving the efficiency of early star formation and the concentration of dark matter have been proposed, but they are forcing a reconsideration of how structure forms and how the initial density perturbations from inflation translate into the galaxies and superclusters and voids we see today. And because the Great Attractor and Laniakea are themselves the products of structure formation starting from those initial conditions, anything that revises our understanding of early structure formation potentially revises our understanding of why the Great Attractor exists and why it is located where it is. Let us come back to what this means for the experience of being here, of being in the Milky Way, of looking up at the night sky and knowing what we know. Every star you can see with your naked eye is, in cosmological terms, your immediate neighborhood. The nearest star, Proxima Centauri, is 4.2 light-years away. The Andromeda Galaxy, just visible to the naked eye on a dark night, is 2.5 million light-years away. The Virgo cluster, which anchors the near end of the flow toward the Great Attractor, is 53 million light-years away. The Great Attractor region itself is 220 million light-years away, 12,000 times the distance to Andromeda. The Shapley supercluster is 600 million light-years away. The Vela supercluster is 800 million light-years away. The edge of the observable universe is about 46 billion light-years away in every direction. Our galaxy is a dust mote in a wind of something incomprehensibly large, and the thing dragging that dust mote is the accumulated gravity of 100 million billion suns, arranged by quantum chance into a structure that grew over 13 billion years, shaped by forces that we understand well enough to name and poorly enough to be humbled by. The name we have given it, the Great Attractor, sounds dramatic, almost theatrical, but it is, when you look at the numbers, deeply literal. It is great, a concentration of mass spanning tens of millions of light-years. It attracts, not metaphorically but physically, with gravitational force that overcomes the expansion of the universe on the scales it dominates. And it is attracting us. Right now, at 627 kilometers per second, carrying our galaxy and everything in it toward a destination that the expansion of the universe may prevent us from ever reaching. This is where the story of the Great Attractor arrives at its deepest implication, the place where physics becomes something that touches the part of the mind that asks what all of this means. We did not choose our trajectory. Our galaxy did not decide to move toward the Great Attractor. It is doing what physics requires. responding to the gravitational landscape laid down by the distribution of mass across hundreds of millions of light-years, which was itself determined by the pattern of quantum fluctuations in the inflationary field, which was itself determined by whatever set the initial conditions of the universe, which takes us to questions that physics currently cannot answer. We are passengers. Every human being who has ever lived, every civilization that has ever existed, every story told around every fire, under every sky, all of it is taking place inside a galaxy that has been falling for billions of years toward a gravitational attractor it may never reach, pushed by a void and pulled by a supercluster, embedded in a larger supercluster that itself is not gravitationally bound and will eventually dissolve, in a universe that is accelerating away from itself at an ever faster rate, heading toward a cold, dark, empty future that will obliterate every trace of the structure we can see today. And yet, here, in this brief window, this cosmologically momentary epoch, when the universe is structured enough to produce observers and transparent enough for them to see the structure that produced them, we have figured it out. We have measured the velocity of our galaxy against the CMB. We have mapped the supercluster that contains us. We have found the void that pushes us. We have detected, perhaps, a dark flow caused by something beyond our cosmic horizon. We have given a Hawaiian name to our home supercluster and traced the flow lines of 100,000 galaxies to its watershed. We do not know if we will ever reach the Norma cluster. We do not know if what lurks behind the zone of avoidance will ever be fully visible to us. We do not know whether Kashlinski's dark flow is a signal from beyond the edge of the observable universe, or a systematic error in difficult data. We do not know what set the initial conditions that produced the Great Attractor at this particular location in this particular configuration. We do not know if the dark energy tearing the universe apart is a constant or whether it will change and what that change might bring. What we know is that we are moving 627 kilometers per second in the direction of Centaurus, toward something that has been pulling at us for longer than the Earth has existed, across distances so large that our fastest spacecraft would take hundreds of billions of years to cross them. We know it because the oldest light in the universe, the faint microwave glow of the Big Bang, is 0.002 of a degree hotter in front of us than behind us, and that temperature difference is a speed, and that speed is a story, and that story is our address in the universe, written in physics so deep and laws so absolute that it will be true for every observer anywhere in Laniakea for as long as Laniakea exists. Something is dragging our galaxy into the dark, and now you know its name, its structure, its origin, and what it tells us about where we came from and where we are going. The dark is not empty. It is full of mass, and the mass has been calling to us since before the first star.